Okay, that's all about time-stepping methods. All right, so we're multi-step. Consistency and stability. We already talked about this for one-step methods. How you can check if a one-step method is consistent, and what is the order of accuracy, and also is a one-step method stable. So now we just need the same criteria for multi-step methods. Okay. Now, so similar definitions as before, that multi-step method is consistent if its local truncation error, so previous tau n at h, goes to 0, as h goes to 0. Exact same definition as for one-step methods. And the order of accuracy is equal to P if the local truncation error is on the order of h to the p. So in other words, if it can be bounded by a constant times h to the p, that's the order of accuracy. Okay, and in this section, I think I don't have the general conditions for order of accuracy. Okay, I have them over here. Okay. I'll get to that later. Okay, so that's okay. In fact, I'll just do all my talk about. Okay, give my formal definitions first, because usually the way it works with one-step, multi-step methods, I can give you the definition, and that might not really help you very much by itself. But then, how we apply the definition to particular methods, and then we can get simple criteria to check, and that's what happens with multi-step methods. A multi-step method is stable, and in the case of multi-step method, there's a synonym for this. It's also referred to as zero stable. And the term zero stable will become clear later on when we come up with a simple way to check stability for a multi-step method. So if I describe the definition is given best given informally. That if you have a small change in the starting values, because remember, a multi-step method needs a one-step method to compute starting values first, like using 4-fold marker cutoff for first few values. Leads to a small change in a numerical solution. So in other words, the equation I can give that the difference between two numerical solutions at the same time, like yn minus zn, is less or equal to some constant k times a max over the maximum difference of any of the starting values, because a multi-step method requires these starting values to be generated by a one-step method before the multi-step method itself kicks in. So with one-step methods, our criteria is a lot simpler to state. It's as if you have a small change in the initial value, that does not lead to some large change in the solution. Here we have to consider not only the initial values, like the initial data for the ODE, but any starting values that were computed by a different method before the multi-step methods started taking effect. So as long as that's the case, as long as we don't have a tiny change leading to some blow up in the solution, then we could say that the multi-step method is stable. Okay, so now we have our formal but useless definitions, and now we can get to our less formal and very helpful criteria for checking consistency, order of accuracy, and stability. Okay, so what I can do is, first for consistency, I'm going to get the local truncation error for multi-step methods. And we'll use a general form of a multi-step method for my notes, not what the book does, because what the book does is stupid. We have our y's that are combined linearly using these coefficients alphas. And then we have our f values combined linearly using these betas. So there's conditions on the alphas and betas that we use to easily determine the order of accuracy and also get a formula for the local truncation error. Okay. So let's see. That's for I want to make sure I have my indices correct here. Okay. All right. So the so I can define these constants. C0, C1, C2, and so forth by the following. So I'll define C0 to just be the sum of all the alphas. And then C1 is going to be, all right, so I have S minus I alpha I, and then the second sum will be the sum of all of the betas, and C2 will have sum of S minus I squared over 2 factorial alpha I. And then here I have S minus I beta J, over beta I, rather. Okay, so this keeps going. So the general form is CQ is equal to the sum of S minus I to the Q power over Q factorial alpha I. And then going to have the same thing to 1 power less. for the betas. And this definition makes sense except for Q equals 0, but we have that case covered here. Okay, so we can define all of these for up to whatever index we want. Now, where these come from, these crazy formulas, and I have this fully derived in my textbook, and well, I do have like a description in the notes. Okay. These come from the coefficients of h to the q in the Taylor series expansion of the, well, basically we plug into the method. Okay. Okay. Because you have, and you're expanding around Tn. So what happens is, when you're plugging in y of Tn plus 1, or y of Tn minus 4, n minus 2, you can Taylor expand all of those around Tn. And these expressions, s minus I to whatever power, those come from different multiples of h that are featured in your method. Okay. Now, so once you figure out all of these coefficients up to a certain point, then it becomes very easy to determine the local truncation error of a method, and therefore its order of accuracy. So what you get is the multi-step method is consistent if and only if C0 and C1 are 0. So that's at minimum, because at least then you have local truncation error that is of order h. So you have order of accuracy P if C0, C1, C2, etc., all the way through CP are all 0. So what that means is all the in your local truncation error, what you have is that all the coefficients of a Taylor series expansion involving terms of order h to the p or less are equal to 0. So the leading term has order h to the p plus 1. But that's in your Taylor expansion of a method. In local truncation error, you would divide by h. Bless you, bless you. So that gives you local truncation errors of order h to the p. So then, your local truncation error is Cp plus 1, the first coefficient that does not disappear, times the derivative, p plus first derivative of a solution at an unknown point, times h to the p. So basically, to get the order of accuracy of the method in local truncation error, you just keep computing C0, C1, C2, etc., and hopefully you keep getting zeros. And once you no longer get 0, the last one that was 0 indicates the order of accuracy of the method. The first one that is non-zero leads you to the formula for local truncation error. Okay. So nothing to it. Okay. Oh, and I have had students carry this out on comprehensive exams. So just so you know. Okay. So start memorizing this now. Okay.
Proving this?
Yeah, not proving that, but I give a multi-step method, a specific one, and say, what is the order of accuracy? Yeah. So, yeah, proving this would be an interesting exercise, but no, I wouldn't. Okay. Yeah. Although it was fun actually doing a proof of it for my textbook, so you can read about there. Okay, now I could be a little more specific for Adams methods. Okay, so we have let's see. Well, first Adams-Bashforth, the explicit case. The local truncation error turns out to be minus 1 to the S derivative. Okay, that bugs me. Let's see, this has degree S plus 1. Hold on a second. So here I'm consulting my textbook. Yeah, because unfortunately when I rattle something off from memory, that's a risky thing to do. Okay, and okay. Oh, yeah, but that is what I have. P plus 1. Yeah, okay. Oh, okay. I do need to tweak that a little bit. All right. So, due to conventions of multi-step methods, I have to multiply this with minus 1 to the p over the sum of all of the betas, just because of normalization. Okay. So I forgot about that, but otherwise, that is the correct formula. So I wonder if my formula that I have in my notes for local truncation error, specifically for an Adams method, might be off. Okay. Oh. Nope, it's not. Okay, everything's fine. I'll explain in a moment. Okay, so we have a S derivative of f at some unknown point, an unknown time, over S factorial, h to the s, and then for the constant, actually we have minus h to the s. And then the scaling constant besides the 1 over s, oops, I already have a minus 1 to the s out here. So h to the s. I have the integral from 0 to 1 of u minus 1, u minus 2, all the way to u minus s du. Okay, so that's the local truncation error for Adams-Bashforth method. For an Adams-Moulton method, very similar, because same number of steps, s, the order of accuracy is 1 greater because there's one extra interpolation point. So s plus first derivative at an unknown point. H to the s plus 1, and then we have u times u minus 1, u minus 2, u minus s du. Okay, now, so here's where you get to decipher my brain fart from earlier. Because I wrote this formula, which is correct, p plus first derivative, and then I get down to here, and I think, well, shouldn't the index of a derivative be the same here as for here? Because here's h to the p versus h to the s. So aside from the difference in letters, why is this p plus 1 whereas this is only s? It seems like a contradiction. Why is that not a contradiction?
Is that the interval of a to 1?
Sorry, what? Integral what?
A to 1 or 0 to 1?
0 to 1, yeah.
Yeah, I'm still trying to read
Okay. That's fine. So why is there no contradiction between this and this?
What again? Between what and what?
The index of a derivative, p plus first derivative here versus s as opposed to s plus 1. Because the order of accuracy is basically the same, it's a different choice of letter. So here you have p plus 1 and p. Here you have s and s. Why is that not a contradiction?
Does it have anything to do with like implicit versus
Nope.
explicit?
Yeah, because this applies to both.
Okay.
Okay, well now I feel better, but I didn't see it right away, since you guys aren't seeing it right away either. Okay,
Give us a hint.
think about what you're taking a derivative of.
Oh, is it like B or something? It's
No.
the same.
No. It's y here, but f here. But f is equal to,
Oh, sorry.
Oh, f is the derivative of y?
yeah, y prime equals f.
Ah.
So this is the s derivative of f, it is the s plus first derivative of y.
You said, okay, yeah.
Okay, yeah, so, and I was thinking, oh, we're taking a derivative of something, but they're different things. So, okay, well, I didn't want to spend that much time on it, but whatever. Okay, so, all right, so that is the, okay, so here we have these specialized formulas for local truncation error for Adams methods, that if you were to evaluate this integral, which would just be a constant, that would give a rest of, like for the constant here, you already have this, minus 1 to the s over s factorial, you just need the rest of it from this integral. Okay, but it's already been established earlier that Adams methods, if it's an s-step method, is order of accuracy s, and if it's explicit, if it's s plus 1, if it is implicit. Okay. Now, okay. Now, using these formulas for local truncation error, it is possible to come up with a formula for local truncation error of a Adams-Moulton predictor-corrector method, where you're combining two Adams methods. And it's also, if you're just using like the general definition of local truncation error, that you're basically substituting your exact solution into the numerical method, and then using Taylor expansions to simplify it as much as you can get the local trunc. You can always do that to get the local truncation error. That's just a universal principle, and it's how we define it. Okay, so for a predictor-corrector method, so this this will be kind of messy to do out in full, but I'll just give a main result. So we have, but here I'll also do a special case. We use an S-step predictor and corrector. Now, you don't have to do that. You can use different step methods for the two stages, but here we assume everything. Predictor is an explicit method, so that's going to be order of accuracy h to the s. And the corrector is an implicit method, that's going to be order of accuracy h to the s plus 1. Okay, so what happens is, okay, if a predictor has this form, yn plus 1 is equal to yn plus h sum 1 to s. Okay, and we call the predicted value yn plus 1 tilde, and we use beta tildes to describe the coefficients of the predictor, which is an explicit method. And because it's an explicit method, we start at 1, I equal 1 to s instead of 0 to s. And then the corrector that'll be our final yn plus 1. And then, because we're using it not as an implicit method but a corrector, we have beta 0 f of tn plus 1 y tilde n plus 1. So our predicted value goes in here. And then we have the rest of the corrector method. Okay. What happens is the local truncation error of the overall method is, I'll call it Sn of h, is equal to tau tilde h. This is a local truncation error of a predictor. And this is order h to the s, plus the local truncation error of the corrector. That's the order h to the s plus 1 times beta naught partial of f with respect to y where this is some unknown value that's being added on here. So the local truncation error of a predictor corrector is a combination of the local truncation errors of the individual methods being combined. Now, I should mention that it seems almost like a waste, in a way, to use a higher order corrector, because this error term from a predictor of order h to the s, that's going to be dominant. So you might say, okay, I'm going to use a 3-step predictor corrector. So 3-step predictor, 3-step corrector. So your predictor is 3rd order accurate, your corrector is 4th order accurate. Your overall method will be 3rd order accurate. So it does seem kind of silly. And actually the textbook I pulled this from didn't bother to explain that. But here's something you can do though. This predictor corrector assumes that you take your prediction, plug it into here, compute this. Oops, that should be, sorry. That should be yn plus 1 is equal to yn plus all this. Okay. So you plug this into here, apply your corrector method, and then you're done, and you move on to the next time step. But you have a choice. What you can do instead is you could take this and plug it back in here, so you can, if you want to, iterate. Keep refining your yn plus 1 until it converges. If you don't do that, if you only just correct once and that's it, this is your local truncation error. If you choose to iterate until convergence, then you can get this term to drop out. And then your local truncation error will simply be the local truncation error essentially of your corrector. It'll have a higher order of accuracy. So something to think about, that it might be worth an effort to do additional corrections if you, in fact, actually that make a lot of sense because this part you don't have to recompute. That's set in stone. It's basically like a fixed point iteration involving only this evaluation of f. Okay. So the extra effort involved might not really be all that much. Okay. All right, so questions about predictor-corrector truncation error. Okay. And it is possible to come up with a bound for a global error, like I've done previously for Euler's method, to show that it converges. Okay. All right. So now that I've beaten this dead horse about local truncation error for multi-step methods, what about stability? How can we check stability? Okay. So what you do is, suppose you apply your multi-step method to a very trivial ODE. Y prime is equal to 0. Y t naught is equal to y naught, which we assume is non-zero. Well, if your derivative is 0, what's your solution?
Constant?
Yes.
I'm sorry.
What?
Sorry. Go ahead.
Yes, it's a constant. Okay. You're waiting for some gotcha one word. Okay. Yeah, and the constant will just be y naught. Okay. So what that means is, but the thing is, what would if you use your multi-step method, what would you get? You would have your y values, which would be alpha I, y n plus 1 minus I, must be 0, because if f is 0, the entire right-hand side of your multi-step method is going to give you 0. And this is a recurrence relation. So now if we keep in mind the theory of recurrence relations, there's actually a form for the solution. So yn would be a sum of it'd be a expression of this form, where these are constants, and the lambdas are the roots of what is called the characteristic polynomial of the multi-step method, or also the recurrence relation. And the characteristic polynomial is alpha 0 lambda to the s plus alpha 1 lambda to the s minus 1 plus alpha 2 lambda to the s minus 2, and so forth, all the way down to alpha s minus 1 lambda plus alpha s is 0. Okay. So we just take our alphas, arrange them into a polynomial, and then we go ahead and get the roots. Let's see. Pi ranges from 0 up to the multiplicity of lambda I as a root. So for instance, if you have a triple root, then you can have a term involving just lambda I to the n, and then another term that'll be n lambda I to the n. Oh, okay. And then you may have a term n squared lambda I to the n. So, sorry, so I made a mistake earlier. This goes up to the multiplicity of a root minus 1. Okay. So if all the roots are distinct, you won't have these factors at all. Okay. Now, from this, I can give a very important condition for multi-step methods called the root condition. Okay, so a multi-step method is zero stable if and only if it satisfies the root condition. All right, so, well, there's actually two of them. First of all, we must have the absolute value, in other words, complex modulus, in case it's complex, of all the roots must be less than or equal to 1. So they must be contained within the unit disk in the complex plane. And the second condition is if there's a root that lies on the unit circle, so its absolute value or complex modulus is equal to 1, it must be a simple root. All right. Now, the point behind these two conditions, these are meant to ensure that your solution cannot diverge to infinity. So, exponential decay is allowed. Staying the same size over time for all n is staying remaining constant or stationary is allowed. Or growth of any kind, whether it's exponential growth or polynomial growth, is not allowed. So this makes sure that you don't have like lambda to the n going off to infinity. The second condition is for cases where you might have multiple roots, and you might have terms involving like n lambda to the n, or n squared lambda to the n. Now, if lambda is less than 1, that'll still go to 0, because exponential growth trumps polynomial growth. But if you have a root that's equal to 1 in magnitude, and you have an n or an n squared term, that's still going to go off to infinity. So we have to disallow that also. So these two conditions together make sure that we will not have any kind of growth in a solution over time. Okay. Now, one important thing though is for any consistent multi-step method, lambda equals 1 is always a root. And the reason for that is one of the requirements for consistency is that the sum of the roots is equal to 0. Well, that is the characteristic polynomial when lambda equals 1 is plugged in. So you're always going to have that. You just have to make sure that 1 is not a double root. Okay. All right. Now, I can refine this definition. So if it is stable, there are two kinds of stability. A method can be strongly stable, meaning that lambda equals 1 is the only root. That is on the unit circle. So for instance, you do not have like -1 as a root, or I or minus I as a root. On the other hand, if this does happen, then the method is weakly stable. So you have multiple but still distinct roots satisfying if the absolute value of lambda is equal to 1. So that's where a case where you have 1 and -1 both as roots, for example. So it is still zero stable. It's still something that can converge. It's just not the kind of stability that you like. Because what happens is you might get some oscillation in your solution, and maybe you don't want that. Maybe you just want to decay straight to 0. Okay. Now, Adams methods, regardless of explicit or implicit, they all have the same characteristic polynomial. You have lambda to the s minus lambda to the s minus 1 is equal to 0. That's your characteristic equation. So, what are the roots of that? Well, how can you factor that?
I mean, factor
Yeah. So you factor out lambda to the s minus 1, and what you're left with is lambda minus 1. So what are their s roots altogether? So what are the s roots taking into account multiplicities?
So 0,
1 and 1. Yeah, so the roots are 1 and then 0, 0, 0, s minus 1 times. Dang it. Okay. So, what's the stability of an Adams method? No. It is strongly stable because, there's an equals here. So, you're allowed to have multiple roots, but not on the unit circle. Yeah, within it, we don't care what happens. So because we have only the root lambda equals 1 is on the unit circle, and it's a simple root, then we can conclude strongly stable. Okay. All right. Okay. Now, so now I'm going to give an example of a multi-step method that is not an Adams method, and it's not a BDF or backward differentiation formula either. And look at its stability. So this method is called Stiffness method.
the same sensor?
Yeah, it's connected to the integration rule.
Okay.
I don't know if the same person developed it, but I guess if not, they were inspired. So this is a straightforward method. We have y plus 1 is equal to yn minus 1. So there's no yn here. Plus h over 3 fn plus 1 plus 4fn plus fn minus 1. Okay, so this is, because we only go back to y sub n minus 1, this is a two-step method. Also, it is implicit, because we have this fn plus 1 here. Now, what's going to be rather surprising is even though it is only a two-step method, you can confirm using the criteria I had on the board earlier in the race, it is surprisingly fourth order accurate. So you might think, wow, this is a dang good method to use. Okay. Now, for a characteristic polynomial, we have alpha 0 is equal to 1 as usual. Alpha 1 is 0, because that's the coefficient of yn. Alpha 2 is equal to minus 1, and then there are no other alphas. So your characteristic polynomial would be, since it's a two-step method, it's a quadratic, so it's so 1 times lambda squared plus 0 times lambda to the first plus minus 1 lambda to the 0. So we just get lambda squared minus 1. So, based on the roots, strongly or weakly stable.
Weakly stable.
Yes, because you have plus and minus 1. So we have more than one root on a unit circle in the complex plane. Okay. So that's unfortunate. Okay. All right, so now with any method, one step or multi-step, what we really want is convergence. We would talk about consistency and stability. But the same rule of thumb applies to as for one-step methods. So a consistent multi-step method is convergent if and only if it is stable. Now, weakly, strongly doesn't matter. So if it's either kind of stability, 0 stable, then we can get convergence. Okay. Okay, 20 minutes. All right, now, we'll take some time to talk about stiffness. Stiff differential equations can be a real pain to handle numerically, and that's actually one of the motivations behind all my work for stiff PDEs. So, what does it mean for an ODE to be stiff? So the solution, the ODE, is said to be stiff if, I'll try to give a more intuitive definition I can. If this numerical solution, by whatever method you're using, one step, multi-step, implicit, explicit, whatever, requires a much smaller time step, a much smaller h. That is needed to accurately represent a solution. Okay. To give an example of what can cause this, so suppose the exact solution, y of t, has a term in it of this form, e to the minus ct, where c is positive, and in fact is large, so much greater than 1. Now, the thing is, when this happens, this expression is very small. So in terms of the contribution it makes to the solution as far as like for graphing purposes is practically nothing. You wouldn't even see it as part of the solution. What about the kth derivative? Well, you multiply that by so minus c to the k. And that's going to be really large. So what that means is, especially for a higher order method, where you take higher order derivatives of your solution, you have large truncation error. Unless your step size h is so small to compensate for it. Because we always, when we look at local truncation error, the only thing we care about, it seems, is what is the power of h. You might think, oh, everything else in there, which is some derivative of y, some constant, is just something of a reasonable magnitude. So we ignore it. We focus on the h to the p part, and what is p. That doesn't really work well in practice, because if your solution has some higher order derivatives that could be really large, and that can happen with these exponentially decaying terms, they sneak up on you. You might think, oh, this solution looks really smooth, I can represent it using only a few points. I can get away with a large value of h, but you can't. So this other part of your local truncation error, you actually can't ignore. And what ends up happening is the larger kind of terms that appear in your solution, the smaller your h has to be. And this is especially a problem for PDEs, where you have terms of this form of all the different frequencies, from low frequency to high frequency. And that's why the smaller the spatial resolution for your PDE, the more troublesome terms of this form appear in your solution. And therefore, you must use an even smaller h, your time step, to be able to represent a solution accurately. So, so for those of you in the KSS group, that's the problem. That's our dilemma. Okay. Now, to give an example of why it's important to have a sufficiently small h. Hopefully I can at least get through a discussion for one-step methods, if not multi-step. Okay. So suppose y prime is equal to minus 100 y, and then y is 0, is equal to 1. So now we know the exact solution. It's e to the minus 100t. So it decays to 0 very rapidly. So we want to make sure that a numerical solution at least decays to 0. It has the correct qualitative behavior. So let's use Euler's method. So that means yn plus 1 is equal to yn minus 100h yn, just filling in what your f of ty is. So it's equal to 1 minus 100h yn. So basically, your previous value is just being multiplied by that to get to the next value. So what should you pick for an h? Let's pick something reasonable, like h is 0.1. Well, yn plus 1 is now equal to minus 9 yn. Well, that's not going to work well at all, because then your solution, your numerical solution, is minus 9 to the n. Exponential growth and oscillation, whereas you're supposed to get exponential decay. But then if you choose h equal 0.001, then yn turns out to be 0.9 to the n. So at least you get exponential decay. It's still rather slow rate, but it's on the right side of behavior qualitatively. And you should, if you choose an even smaller h than that, then you will start to see something that behaves more like e to the minus 100t. So this gives you an idea as to how you have to be careful when you have when your time derivative f can be large compared to y, like if df dy is large, then you need a smaller h to offset that. Now, this is an example of the test equation, which is very useful for analyzing the behavior of numerical methods. Y prime is equal to lambda y, and the real part of lambda is negative, which would imply exponential decay. And y of 0 is 1, so your exact solution is just e to the lambda t. So you can try your method on an equation of this form and see for what values of lambda does it give you the correct behavior. So what happens is, for a general one-step method, applied to the test equation, what you get is yn plus 1 is equal to what there's some function q of h lambda times yn. So all one-step methods will have this form when you apply to this equation, and you have this function of h times lambda together. And q is a polynomial if the one-step method is explicit. It is a rational function if the method is implicit. All right. Now, the key is you have to choose h so that the absolute value of q of h lambda is strictly less than 1. So that is your criteria to overcome stiffness. It just gives you an idea as to how to choose h, depending on some estimate of how big lambda can be for your particular ODE. You can think of lambda as some sort of bound on the size of df dy. Okay, so let's see how much time do I have. Okay, so I'll do an example for a one-step method. right. The modified Euler, also known as the explicit trapezoidal method. Okay, so that is yn plus 1 is equal to yn plus h over 2 f of tn yn plus f of tn plus h yn plus h f of tn yn. So now, if we use a test equation, f of t y is equal to lambda y. So I go ahead and plug that in. So I have yn plus 1 is equal to yn plus h over 2 lambda yn plus, and then here I get lambda times this. So lambda yn plus h lambda yn. So every occurrence of f is just lambda times its second argument. So what I can do is multiply all this out. Plus, okay, so I have h lambda over 2 yn plus h lambda over 2 yn again, plus h lambda, so h lambda squared over 2 yn. Okay, so I can simplify this by factoring out yn. I get 1 plus h lambda plus 1/2 h lambda squared yn. So this is my q of h lambda. So I need to make sure that this is less than 1 in absolute value. Now, it's kind of a pain to figure it out where lambda is allowed to be in a complex plane. But let's assume that lambda is real, just for simplicity. So I need this to be less than 1. Okay, so I have a conclusion here, but I'd rather just work it out. Okay, 6 minutes. So we want 1 plus h lambda plus 1/2 h lambda squared to be less than 1 and greater than minus 1. Okay, so if I subtract 1 from all sides, so I have now, lambda is assumed to, because the real part is assumed to be negative. So, okay, so this whole expression, first of all, has to be negative. Now, h lambda is negative, but what if h lambda squared is so positive it overcomes it? So I have now this is negative, but this now has to be positive to make sure the whole thing stays negative. So I have okay, so then I have 2 plus h lambda. Okay, so h lambda okay. Must be greater than minus 2. So, so as a necessity, I must have this condition satisfied to even have a chance of this whole thing having less than 1 in absolute value. Now, what this means is the larger lambda is, the smaller h has to be to compensate. So if you choose h to be too large relative to lambda, you're not going to get, even though this is a second order accurate method, you're still not going to get the correct qualitative behavior. So your solution could blow up. All right. Let's see. All right, I have too much to say about multi-step methods, so I'll stop there. Okay, so we'll deal with that, and actually made good progress today, so maybe we'll get lucky and we can wrap up on Monday, but we'll see. No promises.